In the last class, we ended by realizing that the z-formula we have learned previously cannot be used to test hypotheses concerning mean scores, because we need to find a way to estimate the variance in standard deviation for groups of scores, not just for a single individual score. This class will focus on how we do that and how we modify the z-formula to test means. Helping us out of the dilemma raised in the previous slide is the central limit theorem, a very famous core part of statistics, which I'll encourage you to memorize. The CLT, or central limit theorem, focuses on the sampling distribution of the sample mean. In earlier slides, we talked about sampling distributions. They are the distributions of sample statistics under conditions of repeated or infinite sampling. So what the central limit theorem does is to tell us what happens to the sample mean if we were to draw an infinite number of samples, all with the same sample size. The first thing the central limit theorem says is that the mean of this sampling distribution of means after infinite sample will actually be equal to the population mean. I don't mean it'll be off by 10 or 15 or 8 or 6 units. I mean it will equal the population mean. The second thing the central limit theorem says is that the variance for all the sample means around the population mean will be equal to the variance of the test divided by the size of the sample, n. Thus, the variance of the test must be adjusted by the size of the sample. As we raised in a previous slide, the variance of a group or sample statistic is smaller than the variance of single scores. You might wonder why this is. The reason is that sources of random error in sampling just one individual from a population is much greater than the sources of random error in sampling a group. Thus, while an individual can vary wildly from the population, the way in which any one person deviates from the population is reduced or essentially washed out when we include others in the sample. Let's continue with our discussion of the central limit theorem. The third thing the central limit theorem says is that the standard deviation of the sampling distribution of sample means is equal to the standard deviation of the test divided by the square root of the sample size, or the square root of n. This standard deviation is called the standard error of the sample mean, or the standard error of the mean. Remember in earlier lessons, earlier classes, that we said a standard deviation of a sampling distribution is called a standard error. That's what we have here, the standard error of the mean, which I've symbolized with sigma sub m, in which m indicates the mean of a sample. The fourth thing the central limit theorem says is that the shape of the sampling distribution of the sample mean is symmetrical and becomes increasingly normal in shape as n increases. The important thing here is that this holds even if the underlying sample distribution is skewed. Although it is a bit of an overstatement, as n increases, we have greater and greater confidence that the underlying distribution of the sample mean is normal. Many authors will cite a sample size equal to 30 as a general indicator that the sampling distribution of the mean will be normal or relatively so, although you should be aware this is not universally accepted. So we have learned that we need to modify the z-formula when we are dealing with samples and with mean scores. And the central limit theorem describes important properties we need to keep in mind when adjusting the formula. So our new formula becomes z is equal to the sample mean minus the population mean divided by the standard error of the mean. So here x is replaced by the sample mean, and the standard deviation of the test in the population is replaced by the standard error of the mean, which is nothing other than the standard deviation adjusted for sample size. Before going to the next slide, please recompute our problem using our new formula. To remind you, we suggested that in the population of depressed adults, the mean of the Beck Depression Inventory is 17 and the standard deviation is 10. We drew a sample of 25 individuals from this population, and at the end of treatment we found that the sample mean equaled 12. The research hypothesis is that the sample mean is lower than the population mean, or that people going through the treatment are less depressed than the population. And the null says that the sample mean equals the population mean. So the question is, do we accept or reject the null hypothesis? Well, we get a very different answer now. Using the new formula, z is going to be equal to 12, the sample mean, minus 17, the population mean, divided by 2, the standard error of the mean. So our test statistic is now a negative 2.50. Z is negative 2.50. Remember, the standard error of the mean is the standard deviation of the test in the population divided by the square root of the sample size, or 10 divided by 5, which is equal to 2. So our test statistic, or calculated value, is negative 2.50, and our critical value remains the same, plus or minus 1.96. Now our test statistic exceeds the critical value, and we would reject the null hypothesis, as the test statistic falls in the region of rejection. In fact, if we consult the z-table, the probability in this problem of receiving a z-score of negative 2.50 or less is 0.0062. Thus, we would conclude that the mean of the treated group is lower than the population mean. We would also be able to assert that this group is no longer from the population of depressed adults, which has a mean of 17 on the BDI. Rather, it belongs to a new different population, which we might refer to as the population of depressed adults who were treated for depression. And our best guess of the mean of that population is currently 12, or the mean of the sample. In an earlier class, we said that power would increase, the power of a test would increase if sample size increases. Let's use the example we just went through to demonstrate this principle. Notice what would have happened if our sample size had actually been larger than n equals 25, rather it had been a sample size of 100 participants. In that case, the standard error of the mean would have been 10 divided by the square root of 100, or 10 divided by 10, or 1. The result would have been that the test statistic would have been 5, z equal to a negative 5, instead of z equal to negative 2.5. So while the numerator stays the same, the denominator becomes smaller, making the test statistic larger. At any time we can increase the value of the test statistic, we make it easier to reject the null hypothesis and thus avoid a type 2 error. Unfortunately, we're usually not able to use the z to test mean differences between groups because the z formula relies on us knowing the variance and standard deviation of a test in the population. As a result, we need to rely on other statistical methods that will allow us to estimate the variance in the population and ultimately to estimate the standard error of the mean. This is where the t and f statistic come in. We'll start by focusing on the t-test in the next class and for a number of classes subsequent to that.